And alright, so my plan today is to talk in detail about pulse width modulation and about Lab 5 and about embellishing on the note that I posted on Tuesday and the video that I made. I also talked to Izad and we updated the lab as it appears on ENGRCS.com, so if you re-download the lab you'll see additional instructions on there that go along with what I posted in the announcement and in the video. But I want to go through all of that in detail, talk to you about some aspects of how you can do Lab 5 most successfully. And then I'm going to go on and talk about the rest of the timing system. We'll talk about the other timers briefly. We'll talk about timer 2 in detail. We'll talk about the hardware subsystem inside the PIC that can actually generate pulse width modulated signals automatically. And then I'll catch up on some other things like reset operations, watchdog timer, rotate instructions, and round it out. And next week we'll start talking about A to D conversion, which will take us through our last lab. And that's week 7, so we're going to have 3 classes, including next Tuesday. So we'll talk about indirect file registers, which is basically pointers that we do in C. Well, we'll look at how pointers are implemented in assembly language. And then we'll probably wrap up by talking about floating point operations and arithmetic operations. And that will probably do it for the course. So before I get into all of that, are there any questions up front? All right, well, let's start talking about Lab 5 in more detail. And let me go to it from the website. Alright, so we'll go through this code in the beginning later on, but I'm going to show you sample code that I put together in MPLAB. But let's look at the actual experiment once more. Your goal is to generate a pair of signals and constantly keep generating those. Your main program is just an infinite loop, just main branch to main. But based on your response to interrupts, you're going to generate a pair of signals. Okay, one signal, which is going to be constantly generated, is RB0. Right, so RB0 toggles every quarter of a second. Goes high, goes low, goes high, goes low. That's just a fixed signal that you're going to constantly generate. Additionally, RA0 is going to be generated with a frequency of 250 Hertz, so 4 milliseconds for one cycle, high to low, high to low, high to low. So it'll be nominally high for 2 milliseconds, low for 2 milliseconds. But RA0 is a signal that you're going to change the duty cycle on. So RA0 might be high for 2, low for 2, it might be high for 3, low for 1, it might be high for 1 and low for 3 milliseconds, or it might be on all the time, or it might be off all the time. Okay, you're generating 2 signals simultaneously. You're generating RB0, which toggles every quarter second, so it's high for a quarter, low for a quarter. So it has a frequency of 2, right? It will go up and down twice per second. RA0 will go up and down 250 times a second, But the amount of time it's high, the amount of time it's low, that's your duty cycle, and that corresponds to your power. And that's the pulse width modulation business that I talked about in the video. Alright, so that's the intended output. Let me show you some sample code that I just put together to look at how we can generate an output with a different duty cycle. Okay, and I want to make sure we nail down some terminology. So if we have a waveform like this distance, this is the period. It's a measure of time. Okay, it's how long it takes for the cycle to repeat. Has nothing to do with how long this is high and how long it's low. It's how long it is from when it goes high to the next time it goes high. It's also the same as the amount of time from when it goes low to the next time it goes low. Okay, it's just the width of one cycle. The frequency is 1 over the period. And it's the number of cycles per second. That's what a hertz is. It's a cycle per second. So when we say that we want to toggle every quarter of a second, right, that means go high after a quarter of a second, go low after a quarter of a second, go high. You're talking about a period of half a second. If your period is 0.5, your frequency is 1 over 0.5, which is 2 cycles per second. Alright, this I'm going to call tau sub h. That's the high time of the signal. And this I'm going to call tau sub L. That's the low time of the signal. So your period is just the sum of those times. Your duty cycle is the time that the waveform is high divided by the period. So if you want the mathematical version of all of this business, there it is. Okay, duty cycle is the part of the entire period during which the signal is high. Sometimes that changes in other textbooks, other contexts. Sometimes the duty cycle is based on the low, but for us it's the amount of time it's high. So 100% duty cycle would be high for the entire period. 10% duty cycle would be high for only 10% of the period. Alright, any questions about that? Because those are our core definitions. And I'm going to use these notions in this code that I want to run through with you.
Is duty cycle like a percentage?
You can express it as a percentage. That's how it's usually done. So when we do 75%, you can translate 75% to what decimal? 0.75. So that's literally saying that this divided by that is 0.75. But we usually think of it as a percentage of what percentage of the period is the signal high. And it turns out if we hook this up to a motor and we have 75% duty cycle, the motor will spin at 75% full speed. If we hook it up to a light, the light will burn at 75% full intensity. Or that's the appearance of it at least. Alright, so I want to run through some sample code, and there's a few reasons for this. One, I want to give you another look at setting up timers and interrupts. Two, most particular to Lab 5, I want to look at how we can use interrupt-driven code to generate a signal with a varying pulse width, a varying duty cycle. Okay, we're going to generate a signal with a fixed period, but we're going to change the duty cycle in software. And that's what you're doing depending on what power you want to deliver. And then 3, I want to show you how you can use some of the tools inside MPLAB to help analyze what's going on and to do your observations, to demonstrate your code's correct working and take screenshots and turn that in for your lab to get credit for the observation part. Okay, and the whole goal of the observation part is I'm not there in lab so you can demonstrate your circuit to me, right? So you need to do your own documentation and put it in your lab report. So I'll show you how we can do that with MPLAB to deal with pulse width modulation. All right, so let's fire this up. And I already wrote this code, so you don't have to watch me type it in, but I'll talk you through it. All right. I'm using a pair of variables, count and high part. You don't have to do it like this, but this is just one way that occurred to me to do this. So here's what I'm going to do. Every time I get an interrupt, I'm going to increment a variable that I call count. That's going to count how far I am into my waveform. So in the beginning of history, I'm going to set my output to be high. I'm going to set count to 0. First time I get an interrupt, I'll increment count. Second interrupt, I'll increment count again. Next interrupt, I'll increment count again. So count will tell me basically how far I am from the beginning of this waveform. All right, I have another variable which I'm calling high part. High part says how many counts should I have where my output is high. All right, and then I'm going to have this notion of what the period should be. How many counts should the entire waveform be? And I'm going to set this up as follows. I'm going to initialize count to 0. I'm going to set high part to 1. And I'm going to think of my period as 4. So here's what I'm going to do. I'm going to start off, my output's going to be high. I'm going to wait for one interrupt to occur, and when that interrupt occurs, I'll increment count. When count is equal to high part, I'm going to drop my output low. A little bit of time passes, second interrupt occurs, count is 2. More time passes, interrupt occurs, count is 3. More time passes, interrupt occurs, count is 4. When count is equal to the period, what am I going to do? Reset count to 0, change my output to high. Time passes, interrupt occurs, count goes to 1, equals high part, set the output low. Time passes, interrupt occurs, count is 2. Time passes, interrupt occurs, count is 3. Time passes, interrupt occurs, count is 4. It's equal to the period. I'm going to reset count to 0, set my output high. Okay, I am generating a 1 out of 4 duty cycle. Right, setting my high part to 1 and my period to 4, that's giving me a 25% duty cycle. Now watch what happens if I just change my high part to be 3 and I initialize my count to be 0. Output goes high. Time passes, interrupt occurs, count changes to 1. Time passes, interrupt occurs, count changes to 2. Time passes, interrupt occurs, count changes to 3. It's equal to high part, set the output low. Time passes, interrupt occurs, count equals 4. It's equal to the period, reset count to 0, raise the output high. Now I'm generating a 75% duty cycle. 3 out of 4. So this code I'm going to show you, this is all that it's doing, right? Every time an interrupt occurs, I increment a counter. If the counter is equal to the period, I've hit the end of my cycle. I go back to the beginning of a cycle, set the output high, reset the count. If the count is equal to this variable high part, I'm done with the high part of the signal. I set the output low. And by changing the value of this, I change my duty cycle. Does that make sense? Questions about that? That's my basic algorithm. This is what I would document clearly in the pseudocode part of a lab report. All right, so implementing this is actually not too bad. So here's my high part, here's my count. Those are just file registers. We'll talk about these in a moment. Usual startup, right? Location 0, go to init. Location 8, go to interrupt. Location 20 is my init code. Set up adcon 1 because we're doing digital I/O. I'm going to output on RB3. So I'm going out on RB3. And I'll show you why in a little bit. So I set that bit of trisb to be a 0, and I set the output high to start. Okay, clear my count. That's counting how many ticks I've had since the start of the cycle. And then the usual timer configuration. So enable interrupts, clear the interrupt flag, enable priority levels. I'm setting my timer to interrupt after 100 ticks. Now this is going to control the frequency of my output. Okay, because all of this description that I've been doing, I've been saying get an interrupt, do such and such. Time passes, get an interrupt, do such and such. But how long is it from one interrupt to the next? Well, that's what this timer 0L register determines. And it depends on what the system clock is, what your prescaler is, all of that business. Okay, none of that is going to affect my duty cycle generation. Okay, so I'm just setting it to be 100 instruction ticks from one interrupt to the next. Alright, and then T0con, I'm going into 8-bit mode, no prescaler, and I'm turning the timer on. And then finally I enable global interrupts at a high priority. Alright, my main code is more complicated than yours is going to be. Your code is going to somehow automatically change power level every half second. Well, you're already toggling this every quarter second, which means every half second you're changing RB0 from low to high. Right? So every time that you make that transition, you can go ahead and move from one power level to another. But what I'm going to do is I'm going to use an input pin to choose the power level. Okay, and so here's what I'm going to set up. I'm going to set up RA0. If it's a 1, I'm going to output a 75% duty cycle waveform. If it's a 0, I'm going to output a 25% duty cycle waveform. Okay, this is not what you're doing in Lab 5. This is just demo code. But if you understand what's going on in this code, you can take that and generalize it and morph it into what you need for Lab 5. Okay, we're doing all of the pieces that you need for Lab 5, but with a totally different high-level behavior. So I want to read bit 0 of port A and set my duty cycle accordingly. So my main loop does the following. Copy port A to W, mask off that low bit. If it is 0, I want a 25% duty cycle, I jump down here. And how do I set a 25% duty cycle? Move a 1 into high part. If that bit is not 0, it's a 1, I want to do a 75% duty cycle, so what do? I put a 3 into high part. Okay, so that's just changing, my duty cycle variable. For you, you're going to, if you do something like this, you'll modulate the value of high part every half second through this pattern. Okay, that's separate code. Let's see, question, do RB0 and RA0 need to be synced? But I don't think I cared for this example, so no for here. For the lab, it's probably useful to do that, to keep everything in sync. But RB0 is changing really slowly and RA0 is changing really quickly. So it's not going to make a big difference, I don't think. So I wouldn't worry about trying to sync them. All right. All right, so that's my main loop. Just hang out and read port A and adjust this high part variable accordingly. And we're going to start off, port A is going to be low. It's going to be a 0, so it'll start off at a 25% duty cycle. All right, so this loop is running. It's just sitting there looping. It's not really doing anything unless RA0 changes. But we're going to get interrupted every 100 instructions. Right, after 100 instructions, 156 will increment to 256 and overflow. So we're going to get interrupted. What are we going to do inside our interrupt code? So we'll talk about this stuff in a moment. But main thing, clear the interrupt request, right? Clear the interrupt flag, reset the timer. I want to do this very early on. If I don't reset the timer until down here, I'm going to take more than 100 instruction ticks for my next interrupt. because all of these instructions are going to happen, and then at the end I'm going to say, okay, now wait 100 instructions. So if I really want 100 instructions, I should set this as early as possible, and I should probably set it to something less than 100. That's detailed, nuanced, don't worry about it too much. But that's why I'm resetting the timer register up here. Alright, so what do? We increment the count, right? That's what we were doing on paper. I check to see if we've hit the period. My period is 4. So I move the count into W, subtract 4. If it's 0, in other words, if we're at the end of this cycle, I jump down here to new cycle. What do we do in the new cycle? Set the output high, clear the count, and we're done. Go to interrupt, done. Okay, otherwise, let's see if the count is equal to the high part. So put the count into W, subtract the high part into W. If it's 0, that means count equals high part. We're at the end of the high part of the output. We should send the output low. So I branch to this section labeled go low, which does what? Just clears RB3. And then we go to interrupt, done. Otherwise, if we're not done with the cycle, we're not done with the high part, we just go to interrupt, done. We don't have to do anything else. All we had to do was increment the count and deal with the interrupt. Alright, and then interrupt done is mainly a ret fee. Let me mention these save registers here. So remember, an interrupt can occur at any point in your code. And in my interrupt code, I use the W register. For example, here I put 156 into W so that I can copy that to the timer register. Suppose I move port A into 0 in my main code, and at this point, 0 has my input bits, and then I AND that with a 1. So now the W register has my low bit of port A, and suppose I get interrupted at that point. Well, I'm going to come into my interrupt code, I'm going to do whatever, eventually I'm going to return. My status bit is no longer based on the result of this AND operation. My status bit is probably based on whatever the last thing I did in my interrupt code that affected the status bits. So good habit, in the beginning of my interrupt code, right, I get an interrupt, I go to location 8. I do a go-to interrupt. Go-tos don't change status bits. So the first thing I do here is I copy my status bits into a file register that I call status save. And then I copy the W register into another file register called WSave. And I'm going to restore those before I leave. So last thing I do in my interrupt code is I put WSave back into W. And that will affect the status bits. So the very last thing I want to do in here is copy from my saved status bits back into status. And MoveFF does not affect the status bits. Okay, so now I've restored exactly the context that I had when I was interrupted, and now I can do my ret fee. And ret fee will re-enable global interrupts, and then we're good to go. Alright, so let me put some stimuli here. So I can set RA0 low or high. I've got a stopwatch over here. I've got my variables down here. I'm going to look at port B. Down here at location 0 is my count. And at location 1 is my high part. That's my duty cycle. Let's see, question, you have to put a dot in front of decimal numbers, it is just a preference. So I didn't say radix anything, the default radix is hex. So if I don't put a dot, this would take this as 156 hex, and it'll probably give me an assembly error saying that the argument is out of range. Right, because 156 is too big a number to store in 8 bits. So the period is there making it decimal. Is there a difference between 100 point? Okay, thanks. You're welcome. Alright, so let's go ahead and build this. And I've got an interrupt down here at this, a breakpoint at the start of my interrupt code. So let's go ahead and run this. And let's look at our variables. Okay, my output is high right now. Anytime that this says 8, that 1 right there tells you the output's high. My count is 0. I'm just going to go ahead and tell it to continue until the next interrupt, which we know will be about 100 instruction ticks later. Alright, the output has gone low, our count is 1. Let's take another step, the output is low and our count is 2. Take another step, the output is low and the count is 3. So the signal was high and then low and then low and then low, and if I do another chunk of instructions, the output goes high again, the count is low. Okay, so I'm just going to step through and just take a look at what port B is doing. Right now it's high, low, or let's run it, low, 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 high, and then low 1, 2, 3 times, high, and then low 1, 2, 3 times. Okay, this bit of port B is reflecting our 25% duty cycle. Now I'm going to fire RA0 to go high, and I'm going to step this. Alright, so now port B is high, it's high, it's high, and then it goes low. It's high, 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 and it goes low. High, 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 and it goes low. So this is my 75% duty cycle. Alright, that's the basic setup. So questions about that? Alright, let me show you why we're doing this business with saving our W register and our status registers. Let's comment out those two instructions. Let's move our breakpoint down here to the ret fee. And let's go ahead and run. So RA0 is low. Okay, that's the default. So our high part, our duty cycle, is set to 1. This should never change. Okay. Our main program will continually check bit 0 of port A. See that it's a 0, it'll set this to 1. So we expect this variable right here to always be 1. Alright. So I'm running through, right? My output is low, low, goes high, low, 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 high, low, low, low. Everything looks good. Let's single step. Okay? Let's single step from the return and watch what happens. My high part just changed to a wacky number, 254. Okay, why did it do that? Because something in my interrupt code changed W to 254, right, FE hex, and I was interrupted right before I said move WF into high part. So since W got changed in my interrupt code, I just set my duty cycle to 254, which is meaningless. Now if this was connected to a motor driving a subway train, guess what? Everybody just kind of fell down if they were standing up because the motor just totally freaked out. Okay? So and this is fairly unpredictable. It's a little repeatable in simulation. But, you know, next time I come back from my return, my duty cycle got changed to 0. And the next time through my main loop, it'll get corrected, right? So now it's a 1, and it'll stay a 1. But each time an interrupt occurs, when you come out of the interrupt, depending on where you were when the interrupt happened, you can get strange results. Okay, so the easiest way to deal with this, save everything. And if we do that, then when we start stepping through, right, there's no weirdness. Our high part's going to be 1, it's never going to change. Totally rock solid. Now, yeah, someone points out from 223, this reminds me of multi-threading issues. It's exactly the same thing, right? Multi-threading is basically, depending on the number of cores, it's traditionally, you know, multiple processes running that are interrupting each other, and so you have to deal with what might be going on when you need to change context. All right, so question, what is the point of the interrupt exactly? Well, it's a little bit contrived in this case, right? But presumably we're doing something interesting in this main loop, and we don't want to spend our main loop counting 100 instructions to go ahead and change the output, right? So we're using interrupts so that we can be doing whatever we want, but when it's time to update the output value, we get tossed over to an interrupt routine. We go ahead, we take care of business, and then we go back to what we were doing. Okay, this is how the operating system works. For example, there's nothing in the operating system which is saying, did you hit a key yet? Did you hit a key yet? How about now? Did you hit a key? Right? There's nothing in MPLAB that's waiting for me to hit a key. But if I hit a key, right, an interrupt is generated, and things happen, and eventually, you know, my cursor moves over one spot. So everything is interrupt driven in pretty much all modern systems, embedded systems, operating systems, most complex environments. It's all interrupt based. So the real point here is just to get exposure to that and practice with it. But we can imagine that we're doing something in here that we don't want to, you know, spend time checking to see if you know, 100 instructions have passed. Well, in this case, the interrupt is simply telling me that I've had another one of these amounts of time pass, right? So for lab 5, you're going to want to interrupt every millisecond. Okay, I think that's how it's set up. It's 1,000 instruction cycle ticks, and you're set to a megahertz instruction clock. So you'll interrupt every millisecond. And so after 256 of those interrupts, you want to toggle RB0. Okay, but each of those interrupts is 1 millisecond, and we've got a period of 4 milliseconds. So RA0, you can process the same way we're doing this now. You get an interrupt, increment a counter. If the counter gets to 4, you're at the beginning of a new period, so go ahead and set the output high. If the counter is equal to whatever your high part variable is, then you should set the output low. So this doesn't just come out of here and plug into lab 5. You really need to understand what's going on in this code, think about what you want to do in lab 5, and figure out how to put those together, how to turn this into that. But it's just an example. All right, so, and the switching of the power happens inside your interrupt code also, right? Independent of all of this, right, instead of reading RA0 to know what the power level should be, every time that a half second has passed, meaning that RB0 has gone high and low, every time that happens, decrement the power until you're down to 0, and then increment it until you're up to 100, and then go back to the beginning. And as we talked about Tuesday, right, you can just make a state variable, initialize it to 1, increment it each time. When it's equal to 9, set it back to 1, and adjust your power level based on what your current state is. All right, so let's look at the fun version of the more fun version of this. Let's look at our simulator. So here's RB3, and you can see it's blinking. It's a little hard to tell, but it's off more than it's on. So maybe if I slow it down, this is a little tricky to play with. Yeah, that's hard to tell. But if I turn RA0 high, it looks like it's on most of the time, then it's just blinking off a little bit. Whereas if I turn that off, it looks like it's off and then blinking on once in a while. Okay, there's a checkbox over here labeled PWM. This simulates a motor connected to RB3. It's only connected to RB3. And if you flip that checkbox, you get a little motor spinning around. And the speed of this motor is based on the duty cycle of RB3's signal. So this is going at a 25% duty cycle. If I flip this switch to a 1 to go 75%, you can see it goes faster. And if I drop this back to a 0, it slows down again. So that's 25% full speed, and that's 75% full speed. This may or may not be useful to you in debugging Lab 5, or in convincing yourself that Lab 5 works. But if you change it to use RB3 instead of RA0, you might have some fun with this. Depending on how you wire it up and how ambitious you are. But anyway, that's a visual representation of what pulse width modulation does, right? A low duty cycle is spinning relatively slowly. A high duty cycle is spinning relatively quickly. And we'll play with this more in Lab 6 when we do A to D conversion. Alright, so let me show you one other tool. This is another thing I learned from a student. If you come down under Window and come into Simulator and do Logic Analyzer, you get something that can show you waveforms. Alright, so when you first do this, you just get this empty window. So if you click on the settings, you can pick any pins you want and move them over to be displayed. So I'm going to display RA0, and for me I'm going to display RB3. You're going to want to do RA0 and RB0. Alright, so I'm going to put those into the selected pins and say OK. And I'm going to change my breakpoint to be back to just the beginning of my interrupt code. And I'm going to go ahead and run this. And you can see my output, this is RB3 on the bottom, went high. RA0, it hasn't really figured out yet what it is. And I'm just going to continue. And you can see it building a waveform, right? So the total time scale of this waveform is increasing, right? It's trying to squeeze the whole waveform into this display. But you can see this is a 75% duty cycle, right? It's high, it's low, it's low, it's low, it's high, it's low, it's low, it's low. Now let's fire RA0 to be high and step through, and what do we have now? We have a 75% duty cycle, right? We flipped RA0 to be high, and starting with the next waveform, it was high for 3 counts and low for 1. High for 3, low for 1. And now if I set RA0 to be low again, we're back to our 25% duty cycle. So you should try to capture your waveform showing RA0 and RB0 in a way that shows the change in duty cycle over time, the constant outputting of RB and the pulsing of RA with different duty cycles. You're going to have to play with it. You're going to have to change the scale that you're looking at. You're going to have to, potentially scroll back and forth. You may want to maximize this and squeeze out some of these other windows on the side to get more viewing real estate. Okay, but play around with this and try to demonstrate this kind of behavior. Okay, make it convincing. Don't just turn on a logic analyzer, take a screenshot, and turn in a fuzzy blob. Okay, try to convince yourself by looking at the logic analyzer output that your signal on RA0 is running at 75% maximum power, and then changes to 50%. And maybe, capture a bit of the waveform where it's showing 75% and then changes to 50. And then, go ahead and continue the simulation and capture the waveform where it changes from 50 to 25 and put that in there. And show where it's 0 and where it's 100 and show where it's coming back up. Right? So you're documenting your observations. Your observations that convince you that this is actually doing what it's supposed to do. So that's yet another tool you can use. This is more useful than the GUI that I just showed you. The GUI is more fun once it's working because you can actually watch this thing speed up and slow down. But for debugging and developing, this and just looking at variables are probably your best tools. Okay, this can really, really help you see what's going on. And so take advantage of that. Could we put a link to a video demonstrating our code in our lab report? You can, but I still want you to document it on the actual pages of the PDF. But if you also want to do a video demonstration, that's always good too. But it's actually a good exercise to try to figure out how to present this kind of information. All right, other questions about this? All right, 5-minute break. Come back, we'll talk about the other timers in the timing subsystem, and then we'll talk about hardware pulse width modulation and move on from there. So I'll see you in about 5 minutes.